Hi everyone. In this video, let's take a look at examples of different multi-level cache hierarchy policies and how in each configuration of these you would populate them. This is going to help you in one of the questions of homework 2. Um, Initially, let's assume all the caches are empty, and in each of the policy, the configuration is same. So our L1 has a direct mapped cache with only two indexes or sets, and then our L2 is four-way with four sets again. Initially, everywhere the caches are empty. So, okay, let's look at regex, right? So, on a regex from the processor, uh, L1 is queried for X because it's a miss. It's going to query L2. L2 is also a miss, so we are going to query from the main memory. We bring X into L2 and then into L1. Let's just assume that they're mapping into the first sets here because we don't have real addresses. But in case of real addresses, you will have to figure out which index, based on the index bits, which set is going to be mapped to. Uh, then let's bring X in the exclusive cache. So again, it's a miss in L1, so we look at L2. If it's a miss in L2 again, we go to the main memory. And because this is an exclusive cache, we directly now bring it into L1. Um, and in a non-inclusive, non-exclusive cache, the same thing. Let's look at L1. It's a miss. It's a miss in L2. So you query the main memory. And since the main memory is being queried by L2, you first bring it into L2. And this L2 is going to address the query of L1. So it's then going to send this to L1. So you populate it in both L2 and L1. Now, the same goes for the read write. It's initially a miss, so you check in L1, miss, check in L2, it's a miss, bring it from main memory. Let's say it's mapping to the second set here, and also in L1, so you bring these two here. In an exclusive cache, it's a miss here, it's a miss here, so you'll directly bring it into L1. Again, 9 is similar to inclusive cache in this manner, so we just bring y to both L2 and L1. Now for read Z, again, it's a miss in L1, it's a miss in L2, so L2 is going to first bring it into, bring Z into it. Let's say it's mapping to the set 3 here. Then in L1, we have to create a space because our L1 is full. Let's say Z maps to the first set, so then we make space for it by evicting X here. And since X is clean eviction right now, you simply evict it silently. There is no need to write it back anywhere. You just evict X and then bring Z into L1. Now, okay, so you have to, now again, same for Z in exclusive. You look at L1, it's not in L1, it's not in L2, so you query it from main memory. And because you're bringing stuff directly from main memory to L1 here, you will query for Z from the main memory, but hey, there's no space here. So first let's make space for it. And on eviction from L1, here it is written back into L2 and then Z is brought directly into L1. So in an exclusive cache, because we're trying to maximize the cache space by almost treating L1 and L2 as sort of a combined capacity, L2 acts as a victim cache for L1. So any eviction here, you place that into your L2 cache, even if it's a clean eviction. And in a non-inclusive, non-exclusive, the same thing, miss. So you bring it first into L2 and then now you want to bring it in L1, but there's no space. You create a space because X was clean. You silently evict it without doing anything, and then bring Z into it. Now we want to do a write into X, right? Okay, so for an inclusive cache, because there is no X here, we query L2. X is a hit here, so now we have to bring X into it before we can write it, but we have to create space for it. So again, we evict Z. Uh, and because Z is clean, it's just a silent eviction here, and we want to now bring X here, and then we write it. So we mark it with a dirty bit that there's a new data written here. Now again, we want to bring X into this, so there is a miss in L1 cache. We make space for it by erecting Z into L2, and then we bring L X from L2 to L1. So we evict it in L2, and then we bring it into L1, and then we write it and mark it with a dirty bit. Now let's assume that we have a write back write allocate policy. I should have said that before, and that's why we're doing the writes in this fashion. Um, and so if you notice that when we allocated space for X in L1, we sort of evicted it from L2 because we are again trying to maximize the capacity of L1 and L2. So we don't have to have multiple copies. Now for 9, it's going to be the same. Like first we have to evict from L1 to make space. So because Z is clean, there's a silent eviction, and then you see L2, X is present, so you bring X into L1 and then mark it as dirty. Okay. Then let's say there is a uh, read, uh, let's say read D. No, that's confusing. Let's put it as read A, and then read, or maybe write B. Okay, so now let's see. Let's say A is again mapped into the set 1 here, and mapped into set 1 again in inclusive in the L1 cache as well. So on a read A, first we need to make space for A in L1 cache. So we evict this, and because this is now dirty, you write it back to L2 cache, and then you bring, you bring A here. Uh, in exclusive cache, you query L1, there's no A here, you query L2, there's no A here, you have to bring it from main memory, but again you have to create space, so you go ahead and write it in L2, and then bring A directly here. The same in non-inclusive, you bring first A into L2, then make space for it in L1. So you are going to write back to L2 now because you had a dirty bit, and then you bring A here. Okay. Let's say instead of write B here, actually the next step we have is write read Z. Okay. So again, for read Z in an inclusive cache, because there's an hit here, you will bring it, but you have to make space. So you make space by doing a clean eviction of A, which is evicting it silently, and then bringing Z from the L2. Here again, even though it's a clean bit, you evict it back to L2, and then you bring Z into L1 by deleting it in L2 and then bringing it into L1. Here there is a clean eviction of A, then you read Z from L2 and bring it into L1. Now at this stage, okay, we have a write B. So because B is not a hit in any of the caches, and let's assume B is uh, mapping in, yeah, actually this is a bad example because we have a lot of ways here. Let's assume for some reason for bringing in B we are evicting Z. Okay, so if this was a direct map, right, or maybe for some reasons in between we had multiple operations where there was Z, C, E, F, whatever, and these are not empty. So now for the write B, before we can bring B into L2 cache, we have to evict Z and assume that Z was LRU. So we got rid of Z. And because we are getting rid of Z here, we have to back invalidate, because there's an inclusive cache, back invalidate it in L1 as well. So you invalidate Z from there and Z from here, and then bring B here. And now assume that B is mapping into the second set in L1. So now to make space for it, you have to evict Y and then bring B here and then do a write. So you mark it with a dirty bit. Uh, Again, in exclusive cache, so you, for bringing in B, even if this was, if the other ways were full, because Z was, and this is an exclusive cache, you have greater capacity here, right? So you don't have to evict anything. You simply bring B here. Oh no, sorry, you don't even bring it here, because you make space in L1 by evicting Z back into L2 and then directly bring it into here, and then you do a write here. Then for a 9 cache, um, the same thing. Assume that this was already full. So we evicted. So now to bring B, we have to first evict Z here, then bring B here. But notice that by for when we evicted Z from L2, you did not have to do anything for L1. So the Z can stay here in L1. And then when you're bringing B into L1, because it's mapping to the second set, you just do a silent eviction of Y because it's a clean um, data, and then you just bring B here. Okay, so that's how generally you keep on populating each of these caches. I hope this is clear. Uh, yeah, so let's just take a short recap of what are the things that we noticed. Whenever we do an eviction from L1, if it's a clean data, you just silently evict it from L1 in inclusive cache and in a non-inclusive, non-exclusive configuration. But in an exclusive cache, even though it's a clean data, you evict it back into L2, so that it's quicker to bring it back in the future if there is a read to the same data again. Uh, but in case of dirty bits, even in eviction from L1 for inclusive or non-inclusive, non-exclusive caches, you write it back into L2 because you're using the write back, write allocate policy. Then we looked at back invalidation of Z when we were writing B in an inclusive cache, which is not present in either non-inclusive, non-exclusive cache or in exclusive cache. Okay, that's it for this video.